Today's video is about carbanions, and in this video we are going to be talking about what carbanions are, how they are formed, and how they can be stabilized. These are the three basic things that we are going to discuss in this video. So please pay full attention and make sure you grab the concept to yourself. And before we continue, I would like to remind you that if you are new on this channel, don't forget to subscribe to the channel in order to help us grow. And also don't forget to like the video, share it, and if possible, comment on it. Alright? And finally, don't forget to turn on the notification bell so that every subsequent video that I'm going to release, you have access to them ASAP. Alright, so let's move right into today's content. Carbanions, what are they? Carbanions are organic ions or species that contain a negatively charged carbon atom. Okay, so the basic way you can explain what carbanions are to a layman or someone who has no idea about what they are is just trying to explain it in a way that we wouldn't use small or huge chemistry terms. All right, so that is what I tried to put down here, that they are organic ions. All right, it means that if they are organic ions, it means that they are made up of carbons, hydrogens, like basically hydrocarbons, right? And they have a negatively charged carbon atoms in them. All right, so there can be 5 or 6 or several number of carbon atoms, but then one of them will surely bear a negative charge. All right, so if you see any organic compound or species that has such a property, then you can classify that species or that organic compound or ion as a carbanion. Okay, so now let's talk about how they manage to get the negative charge. All right, we are saying that they have a negative charge on them. How do they get it? The negative charge is actually placed or added to that particular carbon as a result of the removal of a hydrogen, sorry, the removal of a proton. All right, yeah, the removal of a proton attached to that carbon. All right, so for example, if you follow the case very well, if I would like to use the methyl carbanion here as an example, you realize that this carbon has three hydrogens surrounding it, right? So let's picture it in this way, that initially it was having 4 hydrogens attached to it. So let's say this is maybe uh, a methane, right? Good. So it has, let's say initially it has 4 hydrogens attached to it. But then how come one of the hydrogen left and then we are now having a negative charge here? You know, hydrogen usually has 1 electron on its outermost shell, right? Good. And before a hydrogen can form a covalent bond with carbon, it needs to be able to share that uh, electron with a carbon so that they can form a covalent bond. Is that not it? Good. Now, if you are following very well, every dash in organic chemistry represents what? 2 electrons. That is, for a covalent bond, it represents 2 electrons, right? So we'll say that this negative charge here, okay, was initially not there, all right? And then this bond here was broken as a result of a particular reaction. It can happen maybe through the abstraction of a proton. There are several ways that carbanions can be formed, but then I want to focus on abstraction of a proton, all right? So a base would like to pick this proton off, all right? This is a hydrogen. At this particular time, it is not a proton. Why? Because it's having electrons within it. But as at the time it gets abstracted by a base, it becomes a proton. Why? Because the electrons within it has been donated, or all of them has been given to this carbon. And once it gives the extra electron to the carbon, the hydrogen becomes a proton, and then it can freely be abstracted by a base. Okay, good. So let's say this bond was formed between the carbon and the hydrogen by contributing one electron each, right? But then in order for this hydrogen to be abstracted, it has to give its 1 electron that was used for the formation of this bond to the carbon, right? So the electron in between this bond, the two of them, all of them will be given to the carbon, and now the carbon will have its electron back, and then the additional electron that the hydrogen has donated to it, making what? 1 extra electron for the carbon. That is how come the negative charge. So it makes this carbon negatively charged because the carbon is having an extra electron that does not belong to it. Please, are you following? Yeah, so that is how come carbanions get their negative charge. So we say that the carbanions are usually having a negative charge on a particular carbon atom. All right. Good. Now let's look at the second point. The negative charge gives such organic ions their nucleophilic properties to act as nucleophiles. Of course, if a molecule has extra electrons on it, it becomes negatively charged, right? And any species that is having a lot of electrons in it, we call them what? Nucleophiles, right? You say nucleophiles are electron-rich species, right? They have a lot of electrons to give out. So in a particular reaction, like substitution reaction, carbonyl addition and substitution reactions. Nucleophiles usually act as electron donors, so they donate pairs of electrons for the formation of chemical bonds. Alright, so the presence of this negative charge is what makes them the presence of this negative charge is what gives them that nucleophilic property, that ability to act as nucleophiles. I hope you understand it. Alright, and for me to just mention, the diagram below shows that there can be different types of carbanions, all right, depending on the kind of carbon you are dealing with. If the carbon that you are dealing with has three bonds attached to it, of which all of them are hydrogens, then we call it a methyl carbanion, all right? And if it has at least one alkyl group attached to it, then we call it a primary carbanion, followed by a secondary carbanion where we have two alkyl groups, and here can be a hydrogen, all right? And then when you have three, we call it a tertiary carbanion. All right, so that's how come we have different types of carbanion, and all these ones have their level of stability, and we are going to talk about them in the subsequent slides. All right, let's move on. So there is another point here that says that carbanions are sp3 hybridized. We know hybridization has to do with mixing of atomic orbitals, right? Good. So sp3 hybridization means that we have mixed one s orbital and then three of p orbitals, right? So we have four orbitals over here, of which we have one of them being s and three of them being p, right? So carbanions have that property of being sp3 hybridized, and then as a result of this hybridization, they have a tetrahedral shape. Tetrahedral shape in a sense that, you see, if you look at the diagram here, there are three bonds here, all right, of which the last projection is occupied with what? Lone pairs of electrons. Tetrahedral structures usually have four projections, and when you look at this structure, you see that it has four projections. You have 1, 2, 3, 4, of which three of them are covalent bonds, and then the last one is an sp3 orbital that is being occupied by what? A lone pair of electrons. Okay, so this structure, this shape, the presence of these four projections makes the geometry of carbanions and as a tetrahedral one. All right, so when you go in for a quiz or an exams and they ask you what is the geometry of a carbanion, you should be in a position to say that it is tetrahedral in shape, and also it is sp3 hybridized. All right, okay, now let's look at how they are formed. Formation of carbanions. As I explained in the first slide, all right, this is the best pictorial representation. All right, so there are several ways that carbanions can be formed, but we want to focus on the one that has to do with the abstraction of a proton. Okay, so if you look at the diagram very well, you could see that there are two arrows here, one coming to hydrogen and then the other one moving towards the carbon atom. All right, so this is our initial molecule. All right, this is just an organic compound. This is an aldehyde. Okay, it's an organic compound. As I said earlier on, that carbanions are organic compounds. They are hydrocarbons, right? They are organic ions, is that not it, right? So in order to form a carbanion out of this, we are taking this as our starting material. Okay, so this is an organic compound, specifically ethanol, an aldehyde. All right, and then we have a base here. This base is what is going to do the abstraction. This is what is going to help us abstract the proton from the carbon. Okay, now here we say that the base abstracts the proton. Yeah, so this is our base, and then the base is going to help take this proton off so that we can form the carbanion. All right, but think about this. Look at the base. The base is already having a negative charge on it. Okay, so it is electron rich. It doesn't need any electron from the hydrogen, right? So it has to take the hydrogen in the proton form. Hydrogen in the proton form means that the hydrogen does not have any electron within it, right? So, but look at this. At this moment, the hydrogen is forming a covalent bond with the carbon here. So you would realize that initially here, the hydrogen has what? Electrons. So the base cannot just take it like that. Okay, so before the base can take this hydrogen as a proton, the hydrogen has to donate its electron to the carbon here so that the hydrogen can be free of electron. And by so doing, the base can easily what abstract or take it away. Okay, so that is what the arrow is trying to depict. The bond here represents two electrons. It's a covalent bond. One electron was coming from the carbon and one electron was coming from the hydrogen. But for the hydrogen to be able to break free in terms of a proton, it has to donate the electron that it had. Okay, it has to give its electron back to the carbon. So now this carbon is now having an electron, one extra electron. Okay, it is now having one extra electron on it, and as a result, it's going to be what? Negatively charged, right? Because now electrons are dominating within this particular carbon atom. Okay, and once the hydrogen does that, the hydrogen is also now free of electrons, and it has now become what? A proton, right? A positively charged species. Why? Because there are no more electrons within it. All we can see is what? A proton. Okay, so now this proton will now be free for what? Our base to abstract. So that is what the arrow is trying to represent, right? So the hydrogen, in a simpler way, you can just explain it this way, that a hydrogen gives off its electron that is used in the formation of this bond to the carbon for the carbon to be negatively charged, and this hydrogen becomes what? A positively charged species, and as a result of that, the base easily abstracts it. Okay, so once the base takes the hydrogen, what happens? It forms what? A water molecule. If you look at the product side, you will see that there is a water molecule here. Yeah, so the addition of this proton to the hydroxyl group makes it what? A water molecule. Okay, now because our carbon has now gotten an extra electron, we have now formed a carbanion, and this is what a carbanion looks like. All right, so there are two electrons here, and as I explained earlier on, the carbon had its own electron within this bond, all right, within this bond, and then the other one represents the electron that this hydrogen gave to it. So you realize that the carbon is now having 5 electrons in total, 5 valence electrons. Usually carbon is supposed to have 4 valence electrons, right? But then now it is having 5. Why? Because of the extra electron that the hydrogen gave to it, right? So by virtue of by virtue of the presence of that extra electron, the carbon now gets to what? Have a negative charge on it. So it becomes what? A negatively charged species. That is how come we have our carbanion. Okay, so following the definition, we say carbanions are what? Organic species or organic ions that have what? A carbon that contains a negative charge on it. And this has fulfilled the definition perfectly. Please, are you following? I will be very, very pleased and glad if you can pause the video and try to see if you can explain this to yourself. And once you're able to do that, then it is guaranteed that you have understood how carbanions can be formed in terms of base abstraction. Okay, all right. Now let's move on to the next slide. Now we are going to talk about the stability. Okay, how carbanions get stabilized after they are formed. You know, there are several ways that carbanions can be stabilized. All right, there are several ways that they can be stabilized, and then one of it is through resonance effect. All right. Now what do we have here? A carbanion is stabilized by resonance if a double bond is located alpha to the anionic carbon. Right? If a double bond is located alpha to the anionic carbon. The anionic carbon is the carbon that is bearing the negative charge. All right. So follow the cursor and let's come to the diagram. On your left hand side, you could see that this is basically a hydrocarbon that has a negative charge on one of the carbons, like the one I'm using the cursor to point, right? So let's say this is our first carbon. Okay, for a carbanion to be stabilized by resonance effect, one of the conditions that it has to satisfy is that what? The carbon bearing the negative charge must be attached to what? A double bond that is located at the alpha position to that anionic carbon, right? This is the anionic carbon, and alpha position is just like the carbon that is directly bonded to the carbon bearing the negative charge. I'll repeat myself again. Alpha position is the carbon that is directly bonded or directly adjacent to the carbon that is bearing the negative charge. So if you take this particular structure, this carbon here, the one that is the one that the arrow is pointing to is the carbon that is located alpha to what? The anionic carbon. Okay, good. Now, what is resonance? Resonance effect has to do with um, the fact that we would want to delocalize the electron throughout the molecule. We don't want the electron, okay, the extra electron on this carbon, making it negatively charged. We don't want it to be confined to just this carbon. When it happens like that, the system is not stable. It wouldn't be stable. So in order to make it stable, we would want to what? Disperse or spread this electron throughout the molecule. And when we do that, the system becomes more stable as compared to initially when the electron was confined to just one of the atoms within the whole molecule. Please, are you following? So that is what we are trying to do here. So in order to stabilize this particular system, we don't want the negative charge to be confined to just this carbon, but rather we want to move it and disperse it or delocalize it throughout the system. Okay, that is the concept of resonance. All right, good. Now, how do we do that? As the arrows depict, this negative charge here, as I said earlier on, it represents electrons, right? Good. So we are going to move these electrons in between this carbon, the alpha carbon here, and then the anionic carbon. We are going to move the negative charge here in between them to form a double bond. Okay, we are going to move it here to form a double bond. And once you form a double bond, what happens? This particular carbon, in order to prevent it from forming 5 bonds, all right, because you could see that we have 1, 2, 3, and then there is one hydrogen that we've not written, making 4 bonds already. But if we move this uh, this electron to form a double bond in between this alpha carbon and then the anionic carbon, without breaking this bond, this carbon ends up having five bonds. And when that happens, it has violated the rules in chemistry. In chemistry, carbon cannot have 5 bonds. All right. So once we have brought this negative charge in between these two carbons to form a double bond here, we need to break this bond over here in order to what? Prevent this carbon from having 5 bonds, right? And don't forget the bond here is also what? They are made up of electrons, right? So once you are moving it onto this carbon also becomes negatively charged. Why? Because the electrons within this bond are now moved onto the carbon. So it also has gotten what? An extra electron on it, making it what? Negatively charged. All right, as you can see at the product side. Okay, so you can see that, yeah, the double bond has been formed here as a result of the electron that we moved in between these two carbons. That is what is here. And then the double bond in between the alpha carbon and then the third carbon has now been broken, and then the electrons within it were pushed onto what? The third carbon. That is, as you can see here. So this carbon also becomes what? Negatively charged. All right, this can happen again. It can move back, and then the electron between this bond can also be moved back onto the first carbon. So this process, this to and fro movement of the electrons, makes them what? Delocalize. It prevents them from being confined to one particular atom within the molecule. And when that happens, the system becomes stabilized. All right. So this pair, this and this, now becomes resonance pairs. All right. And usually we use this arrow, this double-headed arrow, to represent resonance. So whenever you see this double-headed arrow in between two species, then you can call those two species resonance pairs. All right. Because they were formed as a result of what? Delocalization of electrons through the process of what? Resonance. Please, are we following? The same thing happens here. When you look at the benzene ring, we don't want the negative charge on this carbon to be confined to this. So we want to delocalize it, we want to spread it throughout the system. So the same thing as I explained in the first one, the same thing happens here. The electron in here is being pushed here to form a double bond between this carbon and then the carbon within the ring, right? And when that happens, to prevent this carbon from having 5 bonds, we break one of the bonds here, the pi bond here, and then we push the electrons onto this carbon so that this carbon can be free and have its 4 bonds, right? So once we break the bond and we push the electrons onto this carbon also becomes negatively charged, as you can see here, right? And now there is another space, there is another possibility that we can push the electron. Why? Because we have another pi bond here, there is a double bond here, so we can freely push this electron back between this these two carbons, and then we break this pi bond off and put it on what, the adjacent carbon again, as you can see here. So once that happens, the other carbon also becomes negatively charged, and then the process still continues. We can move the electrons to form a double bond here, then we break this double bond and put it on this carbon. So it continues until the last carbon. Okay, so you can see that the ability to the property or the fact that we can be able to move this electron throughout the molecule without letting it stay at one place, okay, makes the electron delocalize or disperse throughout the system. And when that happens, we say that what, the system becomes what, more stabilized as compared to initially when the electron was confined to just one of the atoms within the molecule. Please, are we following? I'm very glad you are following. All right. Now let's look at what the second point has to offer. It says that due to delocalization, the negative charge diffuses over the whole molecule and thus stability increases. Of course. So as the negative charge diffuses or disperses throughout the molecule becomes what, more stabilized. Alright. And it says that this explains the stability of allylic and then benzylic carbanions. Alright. So allyl carbanions are carbanions that involves an allyl group. All right, an allyl group is like this group. If you follow the cursor very well, it is having three carbon atoms, of which we have a double bond within it. All right, so 1, 2, 3. This group is what we call the allyl group, and because it is attached to the carbon bearing a negative charge, it becomes a carbanion. So this whole structure is called an allylic what, carbanion. Why? Because it is a carbanion that contains an allyl group. All right. And then the benzylic carbanions, you can see the carbanions that contains benzene rings. All right. So the concept of resonance effect in stabilizing carbanions is very perfect when you use it in benzylic and then allylic carbanions. Okay. Now, in terms of resonance effect, okay, the more the resonance structures a particular molecule has, the more stable that molecule becomes. All right. So you could see that the benzylic carbanions can be more stabilized in terms of resonance than the allylic ones, because the benzylic carbanions can have several resonating structures as compared to the allylic ones. You can see here we have only one of it, right? So if you want to count the number of resonance structures that we have, you have 1 and 2, right? But if you check that of the benzylic ones, we have what, 4 of them. So it means that resonance effect makes benzylic carbanions more stable as compared to the allylic ones. All right. So in order to check or compare between two structures, which one is more stable in terms of resonance, the higher the number of resonance structures that a particular structure has or molecule has, the more stable it becomes. All right, as seen here. So stability increases with increasing in number of resonating structures. So the more your resonating structures, the more stable that particular molecule becomes. Why? Because the more you are resonating the 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 negative charge, the more you are dispersing it throughout the system, the more what you stabilize the system. All right, good. Now let's move on to the next slide. There is another way of stabilizing carbanions. All right, let's see what we have here. The negative charge on a carbanion is stabilized by neighboring electron withdrawing groups like carbonyls, nitro, cyanide, and sulfur. There are other electron withdrawing groups, right? So if you have an electron withdrawing group attached to the carbanion, that can also participate in what the stabilization process. Why? Because they will try to what, withdraw the electron from the carbon in order to what, to reduce the electron density around the carbon. And when that happens, the system becomes what, stable. Okay, this is also another process of resonance. It's also a resonance process. Okay, so as I said, this is a carbanion, and then this is a carbonyl group. Okay, an aldehyde, and this, for that matter, is an electron withdrawing group. So this electron withdrawing group is going to help stabilize this whole molecule by what, removing or trying to reduce the electron density around the anionic carbon, the carbon bearing the negative charge. All right. So let's see what we have here at the product side. So in order to be able to reduce the electron or the electron density on this carbon, this electron withdrawing group is what is going to help us do that. And how is it going to help us? Let's see. The electrons here Okay, the two electrons here making this carbon negatively charged are pushed in between the two carbons, the carbonyl carbon and then the alpha carbon. As I said, this is the alpha carbon and this is the carbonyl carbon in terms of carbonation, right? Or in terms of carbonyls. When we talk about carbonyls, the carbon bearing the oxygen is what we call the carbonyl carbon. And then any other carbon that is adjacent or directly bonded to the carbonyl carbon is called what? The alpha carbon, right? Good. So the negatively charged carbon atom here is the alpha carbon. Okay. Now the electrons that are making this alpha carbon negatively charged are moved, okay, in between the two carbons, the carbonyl carbon and then the alpha carbon to form what? A double bond over here. And when that happens, in order to prevent the carbonyl carbon from having 5 bonds, because initially it has 4, but if we form a double bond here without breaking one of this, it becomes 5, right? So in order to what? Have a stabilized system, one of these bonds, the pi bond, has to break onto the oxygen in order to what? Uh, make this oxygen negatively charged. So when that happens, the electron density here has been what? Reduced as a result of what? The double bond that was formed in here. So the resulting species here becomes an inolate ion. Why? Because now we have a double bond here preventing this carbon from becoming what? Negatively charged. And then the negative charge is now what? Confined to what? The oxygen over here. Right? So you could see that the negative charge here has been what? Moved to the oxygen as a result of what? Resonance. So this is another way of delocalizing electrons within a system. And when you do this, we say that what? You are stabilizing the carbanion. Alright? And then, as I said earlier on, anytime you see this double-headed arrow, it indicates resonance. So these two structures will become what? Resonance pairs. A carbanion and an enolate ion are called what? Resonance pairs. Right? So to put it in a simple summary, we want to reduce the electron density around this carbon. What do? The electrons that are making this carbon negatively charged, we push them here too for the electrons to be shared in between these two carbon atoms. And when that happens, we reduce the what? The electronegativity or the negative charge on this carbon, right? And in order to prevent this carbon from having 5 bonds, we break one of the pi bonds here and put it on what? The oxygen to make the oxygen negatively charged. And as a result of that, we have what? Stabilized the system. And this is what we call resonance stabilization. All right. This can be done by nitro groups. Cyanide can also do it. Sulfones can also help it. It's just like the same process. Just like how we manage to use the carbonyl here, the aldehyde, to stabilize this carbon, the negatively charged carbon atom here. The same way cyanide can do it. The same way a nitro group can do it. The same way a sulfone group can do it. Okay. All right. So I have some trial questions here. I have 2 examples here. If you actually understood what I did in the previous slide, just pause the video and try and see if you can form a carbanion out of this two. We have a propanone and we have the acetonitrile here. You can try and see if you can form a carbanion out of this by using a base to abstract a proton and form a carbanion, and then try to see if you can stabilize the carbanion using what? Resonance. All right. Try for the two, and if you can do it very well and get the answer correct, then it means that you have really understood what I explained earlier on. All right. So after you are done forming the carbanion and stabilizing it, replay the video and then watch the solution. See what I have for you. Compare it to yours and see whether what you had is the same as what I have over here. Once they are the same, then it means that you are good to go. All right. So this is the solution. For acetonitrile, this is how you form the carbanion. As simple as that, as I explained in the previous episode or the previous slide. All you have to do is, this is your base. Your base abstract a proton. How does it get it? The proton has to donate, or the hydrogen has to donate its electron to the carbon so that it can become free of electrons, so that the base can easily abstract it, right? So when that happens, the carbon becomes negatively charged, and that is what you can see over here. In order to stabilize this system through resonance, we need to be able to move this electron in between these two carbons to form a double bond. And to prevent this carbon from having 5 bonds, we break one of the pi bonds here and put it on the nitrogen. And this is what we have here. So this becomes our resonance pairs, and we have a resonance system. This system becomes more stable as compared to what? The initial carbanion. Alright, the same thing applies to the propanone. The base abstracts the proton tries to give its electron to the carbon, making the carbon negatively charged. In order to stabilize the system, the negative charge is brought in between these two carbons to be shared. To prevent this carbon from having 5 bonds, we break the one of the pi bonds and place it on the oxygen to make the oxygen negatively charged. And then now we have a resonance system, 2 resonance pairs. Are you following? Good. Let's see what we have here. Now we are continuing the stabilization process. There is another way we can stabilize carbon ions. Okay. Now let's see what we have here. The stability of alkyl carbon ions can be explained by inductive effect. All right. So carbon ions can also be stabilized through inductive effect. So apart from resonance effect, we can also use inductive effect to stabilize carbon ions. All right. Let's see what we have here. The polarization of a sigma bond due to electron withdrawing effect or electron donating effect of adjacent groups or atoms is referred to as inductive effect. So inductive effect is also similar to resonance. Why? Because it has to do with the movement of electrons, right? Or it has to do with the polarization of a bond where you confer partial and then a partial positive and partial negative charge on a particular atom within the molecule. Okay, but then the difference here is that inductive effect deals with sigma bonds. Okay, inductive effect deals with sigma bonds. It does not deal with double bonds. So once you have a double bond within the molecule, it wouldn't work for inductive effect. All right. The third point here says that it is transmitted through sigma bonds. No pi bonds are involved. Once you have a pi bond attached to a sigma bond, it becomes what? It becomes what? A double bond, right? Yes. So that's why we are saying that inductive effects or polarization of bonds specifically works with what? Sigma bonds. Okay. All right. So let's see what we have here. The greater the number of alkyl groups attached to the carbon atom bearing the negative charge, the lesser the stability of the carbon ion, right? Inductive effect has to do with polarization of a bond. Okay, it also just simply means movement of electrons throughout the system. Electrons can either be moved towards the carbon ion or it can be moved away from the carbon ion. Okay, the carbon ion is already electron rich, right? If you follow the cursor very well, you will see that the carbon bearing the negative charge, as I explained several times, it is already electron rich. So adding more electrons to it will increase the electron density around that carbon. And when that happens, that particular species becomes highly unstable. All right. So in order to stabilize it through the process of inductive effect, we should be able to put groups that would what? Help reduce the electron density around the carbon, right? So in order to be able to stabilize a carbon ion, we need what? A negative inductive effect. We need electron withdrawing groups to be surrounded. We need electron withdrawing groups to surround the carbon ion so that they can what? Move electrons away from the carbon bearing the negative charge in order to reduce what? The electron density around it. Okay. Now we are saying that when you have alkyl groups like methyl, ethyl, most of all of them are electron donating groups. They donate electron into the system. Okay, and then we call it a positive inductive effect. Usually they try to pump electrons into the system, and when that happens, they end up destabilizing the whole system. All right. So following this diagram over here, we want to rank this group of carbon ions based on stability. All right, using the explanation that I just spoke about, that is the inductive effect. So you could see that here, this carbon ion here has what? Hydrogens attached to it. All the projections here are all hydrogens. So it becomes what? A methyl carbon ion. That was what I said on the first page. All right. This becomes a methyl carbon ion. And because all these are hydrogens, they are not alkyl groups. They are neither going to donate electrons or what? Take electrons from the system, right? So because of that, this system is quite stable as compared to this one that has at least one alkyl group here that can pump electron into the system. Once this alkyl group tries to push electron into the system, this negatively charged carbon becomes more negatively charged. The electron density around it becomes so high. Okay, so it becomes what? More unstable as compared to this one that has nothing to do with electron withdrawing or electron donating. Same thing applied to this one. This one has two alkyl groups. It means that these alkyl groups can pump electrons into the system, making it highly unstable as compared to this one. The same thing happens here. This one we have three alkyl groups surrounding the carbon ion, and all these alkyl groups can pump electrons into it, making it what? Highly unstable, right? So the stability here decreases as you increase the number of alkyl groups around the carbon bearing the negative charge, right? So the higher the number of alkyl groups around the carbanion, the less stable the carbanion becomes, as the diagram depicts. So the methyl carbanion is more stable as compared to the primary carbanion, which is also more stable as compared to the secondary. Likewise, the tertiary. Okay, right. So if you have gone through this very well and you paid attention, I'm sure by now you would have understood everything about carbanions, how they are formed, and then how they are stabilized through the process of resonance and then inductive effects. Okay, now I would want to introduce you to some kind of the types of carbons that we have when we are dealing with carbonyl groups. Okay, there are several types of carbons in organic chemistry, and then I would like to just mention a few so that you have that idea as well. Okay. But then before I say that, we have a point here that I need to address. We say that carbanions are usually formed on the alpha carbon due to its ability to easily exhibit resonance, right? As I said, carbanions usually are formed on alpha carbons. Why? Because the alpha carbons, they have this ability to easily undergo resonance as compared to what the subsequent carbons such as the beta, gamma, delta, blah 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 blah. You get it? Now, what is an alpha carbon? As I explained earlier on, when you are dealing with carbonyl groups or carbonyl molecules, sorry, the carbon that is bearing the oxygen, the one that the oxygen is attached to directly, if you follow the cursor, I mean this carbon, this is what we call the carbonyl carbon, as is written here. And then any other carbon that is directly bonded to this carbonyl carbon is called the alpha carbon. So if this hydrogen were carbon, it would have been called what? An alpha carbon, right? But so far as it's not a carbon, you can't name it an alpha carbon, right? Now it's a hydrogen. Yeah. But because this carbon is the one that is bonded to this carbonyl carbon, we call it an alpha carbon. All right, then the subsequent carbons that are attached to the alpha carbon are called what? Beta carbons, like this one. And then the one following it is called the gamma, followed by the delta, followed by the epsilon, and then zeta. It continues like that. There are several ones, but then for the purpose of this video, I'll just bring this to your attention. So for the purpose of this video, and then for that matter, carbanions, we would limit ourselves to this number of carbons. All right, there are other ones, there are several of them, but then we'll limit ourselves to this number of them. But then most importantly, when it comes to carbanion, what we need is our alpha carbon. Why? Because it easily has the ability to what? Undergo resonance, and then we can form our carbanion here perfectly and stabilize it with what? Resonance. All right, good. So thank you very much for watching the video. I'm glad you were able to stay tuned from the beginning till now, and I'm sure you've picked something positive out of this video. Thank you very much. I'll see you in the next video. Bye bye.